Quantum Eraser learns about math and physics in the one-room schoolhouse with room for one. Why don't we set the tone?
We should treat each other with respect, common courtesy, and I think that would go a long way.
I agree. Quantum Eraser, why don't you give me a nonverbal signal if you're ready? Alrighty, let's get started. So this is the second video of a 3-video series. The first one was on experimental design. This one's on math and physics. And the next one's going to be on logic. And all three of these videos are all based on his toe tagging of me, which I'm going to talk about in a few moments. So it looks like QE is excited. Let's get started. So it all started 4 years ago. We'll talk about the origins then. And I'm going to give you my teaching background and the diagnostic approach I use. And then we're going to go over Quantum Eraser's subtraction error. There's actually a little bit of depth there. We'll have a little lesson on significant figures and the phrase, it's exponential. We'll then learn a little bit about scientific notation and then units of pressure and do some dimensional analysis. Then we're going to get into what we're really here for, which is pressure differentials and pressure gradients. That's the star topic. Finally, we'll do a little overview of all the math that we covered, and then we'll cover the first law of rebuttal videos, and then we'll do some lessons learned. Now, this is a long video, so the timestamps are going to be in the description for these 11 steps if you want to skip ahead to any section. So this is a bit of a labor of love. This is actually 231 slides long, and many of these slides are multiple layers, so it's taken me a couple weeks to do this, but I hope you guys will be entertained as well as educated. That's my goal. So, QE versus flat earth math, the origin.
This topic is going to be about Charles' flat earth math. This started 4 years ago, and ironically, on Robert Bassano's channel. This subject came up. I whipped him around by his short hairs, Charles' flat earth math. But he just couldn't let sleeping dogs lie, right? So for the next periodically this is from 2016, folks, on Robert Bassano's channel, like I said. So periodically, when he's been around, he always asked me this question. How do we calculate pressure differentials?
And that is the question. How do we calculate pressure differentials? And so he's right. I have been bugging him every so often over the last 4 years, up into including 3 days before the toe tagging video. And I asked him, how do you compute pressure differentials with division or subtraction? So we're going to cover that in this video today. So 4 years ago, as he mentioned, there was a conversation with Robert Bassano. The channel is Planate, Veritas, and it was about a 4-hour conversation on a whole ton of topics. And Quantum Eraser came in about the hour mark. And so we had a rollicking conversation. But he excerpted about an hour and 46 of this for his own video, which he just published, I guess, about a month ago. Robert Bassano, Quantum Eraser, and Robert Bassano, Charles Flat Earth Math train wreck. So in this conversation, there was a 12-minute chat on atmospheric pressure, and we're going to zoom into this 12 minutes. So in this 12-minute chat, Quantum Eraser has sampled 4 different audio clips, and this entire document is accurate to the pixel. So it shows that he's only sampling things from the very tail end of our conversation, not stuff from the beginning. So we will go over that a little bit later. So he did record a toe tagging video. So he had his panel, and they had a great time making fun of me. And I woke up in the morgue with a toe tag, and I had no idea what happened. But so this is my response to that. So next, my teaching background, specifically the diagnostic approach that I use. So I've been teaching for almost 25 years in the great city of Philadelphia, and exclusively in public schools, exclusively inner city, serving lower income students. And this is the view of the city that I see every single day when I drive home before we had the lockdown for the coronavirus. But I do get to see this every afternoon. But I did get started when technology was a lot older, We had hand-cranked mimeograph machines, and I had a chalkboard, and I loved, my favorite chalk was Prang Hygeia Yellow. If you ever use a chalkboard, that's a great chalk. So what do I mean by diagnostic teaching? This really means trying to help a student who's the student is trying, but the student's difficulty is not in basic arithmetic. So they don't do 2 + 7 = 8. So they know the arithmetic, but they're having a problem somewhere in the logic of it, which means that they actually believe their answer is correct. They're following a procedure. They think they're doing it correctly. Which means they make the same mistake consistently. And we're going to see that in today's video, the same mistakes being made over and over and over again by Quantum Eraser. And the difficulty is that they've learned something, but they learned it wrong. Okay, so they, like I said, it's not arithmetic, but they learned either rules or algorithms, but they learned them incorrectly. So they're going to use that incorrect algorithm, and they're going to think that they're doing just great, except they get the wrong answer. Okay, so here's a little challenge for you. Feel free to click pause on the video if you want to take a look at these 10 problems and see what is the logical error. Again, there's no arithmetic errors. These are all errors that are logical errors where the student thinks they did the right thing and they think they got the right answer. All right, let's go over them now. So number 1, when they got to the tens, they saw 2 - 5, but you can't do 2 - 5. So what did they do? They subtracted upwards. They did 5 - 2. I actually see that. Now here, it's just a misunderstanding of a negative exponent. They're like, well, the answer's got to be negative. So this is just, 5 squared, and then we have a negative, if it's 5 squared. This is a classic one, adding numerators, adding denominators. This one is a little bit more subtle. If I were to say, what is the square of -5? You would say positive 25. So what this person did is they squared -5. They squared -5, and so they're adding, 100 plus 25. Now this one is interesting because they're getting the answer right. So 2 squared is 4, so you think, great, they know exponents. But then you see this one, 3 squared is 6. Clearly they don't understand exponents because they're simply multiplying the 3 and the 2, which means that chances are that 4 wasn't really 2 squared, it was just 2 times 2. They misunderstood the exponent. Number 6, they used a rule which does not exist, the distributive property of exponents over addition. So I see that all the time. You got to use FOIL to multiply that. Now this one comes from a mistaken rule learned in elementary school, and that rule is a negative and a negative make a positive. Right? I can't stand this when teachers teach this rule to students because it's supposed to be a negative times a negative is a positive. But they just thought a negative and a negative. 2 negatives make a positive, so the answer is positive 7, which is wrong. Number 8, they did the long division, but then they got a remainder of 2, which properly expressed should be 2/4, right? Or 1/2, so 14.5. But when they got their remainder of 2 after the long division, they simply copied it as a decimal. And this next one, number 9, they were trying to cancel things out to simplify this fraction. So they canceled out a pair of x squareds. They canceled the -9 with the -3. Unfortunately, that is all illegal. You have to factor the numerator and factor the denominator before you do any canceling. And number 10 is actually a version of Quantum Eraser's error, which we're going to go over in a few moments. So let's take a look at Quantum Eraser's subtraction error. So he made a big deal about how it was saying that he should be subtracting these numbers, and so he did the subtraction, and he got the wrong answer. So Blue Marble Science has a very nice 6.5-minute video detailing this, but I want to go over this now. And my challenge to you was, what was his procedural error? And what I'm going to say is Quantum Eraser used an algorithm to get this wrong answer. In other words, this is not an arithmetic error. Okay, so here's my challenge to you. Feel free to pause the video if you want to try this because it is very clever. All right, let's go over this now. So we'll start with just an analogy. Let's say there's a store and they allow you to buy things with $100 bills. And so you buy a $1.50 item with a $100 bill, and using mental math, what is your change? It should be very straightforward. Bingo, $98.50. Okay, I think everybody got that without even, without actually doing long subtraction. But what if you were to actually do the long subtraction? What would be your algorithm? Let's do the correct algorithm here. Okay, how are we going to solve this using actual long subtraction? So we're going to start at the right. We're going to subtract 0. 0 minus 0 is 0. And then we're going to try to do 0 dimes minus 5 dimes, which we can't do. So we need more dimes. And what we're going to do is we're going to borrow $1 from the $100. So we're going to cross out this $100 and make it $99, giving us $1, which is represented by, say, 10 dimes. 10 dimes minus 5 dimes is 5 dimes. Okay? And now we have $99 minus 1, or 9 minus 1 is 8, and then 9 minus 0 is 9, giving us our final answer of $98.50. Okay, so that's pretty basic math, but the key thing is the crossing out of the 100 and writing 99. You're going to see Quantum Eraser does not do this. Okay, so what I've got here is, and these images are copied from Blue Marble Science. So Quantum Eraser's error is in red, and then the correct answer is in the bottom image. So let's go over exactly how Quantum Eraser got his answer. So this isn't the exact problem from Quantum Eraser. I left out most of the zeros, but you can kind of I can illustrate the point with these numbers. So I had a little bit of trouble initially figuring out what he did wrong because every other digit seemed to be correct. And then with a little bit of thinking, I realized what he had done. So obviously we start at the right, and we try to do 0 minus 8, which we can't do. So we need to borrow 1. So he borrowed 1 from the 0 and made that a 9. It's almost like borrowing 1 from the 10 and making the 10 a 9. And this is what he did. So he put the little 1 there. So that's his 10 minus 8, which is 2. And then we have 9 minus 6, which is 3. Now we have 0 minus 3, which we can't do. So we need to borrow 1 from this and make this a 9, and then make that a 10. 10 minus 3 is 7. And then 9 minus 3 is 6. And again, 0 minus 9 we can't do. So we borrow 1 from that, make that a 9. And then we have 10 minus 9 is 1. And then 9 minus 1 is 8. And then the rest was zeros. 0 minus 0 would be 0 all the way on out, ... And in this case, it's just a 1. Now, if you compare these two numbers, you see that the bottom number is greater than the top number. So we're subtracting, and we end up with a bigger number. And that is the mistake that Quantum Eraser made. All right, now let's take a look at the way we are correctly supposed to do this. So we're going to try to do a borrowing thing to make this 0 a 10, right? We want to make that 0 a 10, but we need to borrow. However, this number is not 10. We can't borrow from this 10. We have to borrow from this number, which is 1,000,000. So we have to borrow 1 from 1,000,000, which means we have to cross this entire thing out. I'm going to crisscross it. We have to cross this entire thing out. Borrowing 1 from 1,000,000 gives you 999,999. Now 999,999 plus 1 is 1,000,000. So we could put that 1 over here and make it a 10. 10 minus 8 is 2. 9 minus 6 is 3. 9 minus 3 is 6. 9 minus 3 is 6. 9 minus 9 is 0. 9 minus 1 is 8. 9 minus 0 is 9. And then you're going to get 9s all the way out, in the original problem. All right. And then again, if you take a look, this final answer is in fact smaller than the original problem. And that's exactly the way you're correctly supposed to do it. But I hope you see that the Quantum Eraser was actually using an algorithm. He just was using the wrong one. So just joking around with Blue Marble Science, he had this on his video. And so I'm just going to say, yes, I am. All right, so here's a challenge for you. 5 shovelfuls of dirt plus 2 shovelfuls and 3 spoonfuls of dirt. What do you get if you use combining like terms? Did you say 7 shovelfuls and 3 spoonfuls of dirt? Because the correct answer is 7 shovelfuls of dirt. Now, what do I mean by that? Significant figures. That's our next topic. So with significant figures, the result of your calculation can only be as precise as the least precise input. All right. In other words, you can't make your result more precise by arbitrarily showing more digits in your answer. And quantum eraser does this all the time. So, for example, in his infamous subtraction problem, the original problem had 4 significant digits. And then he does this big subtraction. You should get 4 significant digits in your final answer. That would have been 14.69. Even if you do the subtraction correctly, again, 4 significant digits to start, you do the subtraction. Even if you did it correctly, you get 14.689999, but then you have to round to 4 digits, which would round to 14.69. So you'd get the correct answer either way. So my dad used to teach fellow engineers when he worked for GE during the Cold War. And so he, in one of his classes, I guess it was on instrumentation or measurement or whatever, he had asked a question like this. But we all know there's 5,280 feet in a mile. So let's say the school is a mile from the post office. How many feet are they apart? And the engineers would all say 5,280, but the correct answer is about 5,000 feet. And they'd all get upset until they realized there was only one significant digit in that problem. All right, so Google Maps reports the distance as 1.0 miles. How many feet apart are they? Then it would be about 5,300 feet. So significant digits are very, very important when you're doing calculations with multiple digits. All right, again, the result of your calculation can only be as precise as the least precise input. All right, let's go on to one of the favorite phrases of quantum eraser is it's exponential. All right, so let's take a look at a carton of eggs. Is this carton of eggs, or are these eggs exponential? And so here's a hint. There's 4, there's 8. Are they exponential? Yes, of course they're exponential because 2 squared plus 2 cubed is 12. And of course I'm being silly. Just because you see an exponent doesn't mean something is exponential, which we're going to go over in a few moments.
Not even talking about science here, just basic common sense. For people to communicate with each other, you have to define terms. Because if you're conversating with one person and you're talking about an amoeba and they're thinking about an orangutan, well, you're going to have a difficult time, not even then, but you can't move on downstream. It's just going to get frustrating because you're talking about 2 different things.
So that's an excerpt of his presentation when he was going up against Blue Marble Science and trying to toe tag him. But I think this sentiment is exactly correct. You want to define your terms. You want to make sure that everyone's talking about the same thing. So we're gonna focus on that. So for example, let's say somebody was communicating, I want you to run the ventilation grill up the side of the building and then stop at the roof line. Or on the right, I want you to cut a hole such that the pipe goes in through the wall. So it's really important to carefully communicate. So these terms are well defined. Obviously, everyone knows what an exponent is. Exponential notation, we've got a whole section on that. Exponentially small, exponentially large, these all make perfect sense. And exponential functions, a lot of people don't realize this. It isn't just raising something to a power. Like, for example, you may have a function that has x squared or x cubed or even x to the 10th. Those aren't exponential functions. The independent variable has to be in the exponent. And so you've got a couple examples of exponential functions. For example, exponential growth. Here is the classic compounding interest formula. Notice that t, the independent variable, is an exponent of e. And then you've got exponential decay, and here's an example of using the half-life formula. And again, t is an exponent of the base. All right, and then also there's a phrase called orders of magnitude, where you're multiplying or dividing by a power of 10. So 5,000 is 3 orders of magnitude greater than 5, or you multiply 5 times, 3 orders of magnitude bigger. All right, now these terms are not well defined. And they come up a lot in quantum eraser's communication. So he likes to say things like, it's exponential. Well, exponential, it just can't be used as a generic adjective because we just went over 7 examples of very specific things that exponential might mean. So which of those 7 do you mean, right? Or this one, exponential moves. This is even worse because moves has no definition. Are you adding? Are you multiplying? Are you raising to a power? So in math, we don't talk about moves. We use other language like adding, subtracting, multiplying, raised to a power, other mathematical operators. math or exponential orders of magnitude. Now, this may seem reasonable, but the thing is, orders of magnitude is already defined. So putting the word exponential in front of it doesn't make it better. In fact, it just muddies the water. All right, so it's kind of redundant and confusing. And then lastly, exponential magnitude. And this may be confusing because it sounds very similar to orders of magnitude, but the magnitude of a number is just the size of the value, ignoring the leading negative. And so, again, exponential is just used as a generic adjective here. So what exactly does this exponential mean? These are very, very unclear what any of these terms means. So again, Quantum Eraser said for people to communicate, you have to define terms or things might get frustrating. So these are well-defined terms, and these are not well-defined. Unfortunately, Quantum Eraser relies on this vocabulary. So earlier in my conversation, Quantum Eraser said, that's exponential magnitudes of pressure gradient. And I said, no, because it wasn't because it didn't have an exponent. I mean, it clearly did have an exponent. It's just that there wasn't an exponential magnitude of pressure gradient. What he meant was pressure differential. So that's why I said no. And then he's like, well, exponent doesn't mean exponential. It's like, yes, it had an exponent. Everybody could clearly see the exponent. But exponential is a generic adjective. Okay. Also, I like to use very clear language. So I said exponentially small. And then he doesn't want me to say exponentially small. He just wants to use the word exponential and have that be a catch-all. All right. And then this one's even worse, exponential difference. Well, the word difference means to subtract. So I'm not quite sure how you could have an exponential difference. Literally that phrase doesn't make any sense. All right. And so he's comparing these two powers of 10, 10 to the negative 12 and 10 to the negative 17. He's just comparing them, but he's like, going from one to the other is not exponential. And it's not really clear, what he's doing here. And then he uses this phrase, and it's an exponential 5 orders of magnitude move. And again, there's no such thing as an exponential orders of magnitude, or at least it's redundant and confusing. And then, of course, the word move, who knows what move means? Move is not defined in mathematics. All right, so let's do a practical example. From 10 to the third to 10 to the negative 2, is this an exponential move? It's 5 orders of magnitude. And you should say, well, I need more information, leaving aside the fact that exponential move isn't even defined. So, well, let's do a practical example of that. You have 1,000 milliliters of liquid. All right, and then you pour it into your experiment. You empty your beaker into your experiment, meaning your beaker is now empty. But if you examine it, you see a couple tiny droplets of liquid, and you estimate it's around 1/100 of a milliliter. Okay, so here we have again 10 to the third, or 1,000, to 10 to the minus 2, or 1/100. So is this an exponential move when you poured your beaker out into your experiment? And the answer is no, it's merely subtraction. You started with a full beaker, you poured it out. That's subtracting. Okay, orders of magnitude is completely irrelevant here. So if you did pour your beaker out and you were left with these tiny droplets, does that mean you can actually determine how much liquid was poured into the experiment? And so you may say, well, let's subtract, right? And what would you get if you subtracted these? Is the answer 999.99 milliliters? No. The answer is 1,000 milliliters. Because of significant figures, there was only one significant figure in the original problem. So 999.99 milliliters, that's too much precision. You can't add more precision that isn't there. Okay? So let's do a kind of a corny example using large and small numbers. Let's say you take planet Earth with 7.6 billion people, and let's say you take each person on Earth and you give that person their own planet. You give each person his or her own planet. And then each planet, let's say you populate every single one of these 7.6 billion planets with 7.6 billion people. Now you take this new universe and you duplicate the universe 30 times. I mean, that's a ridiculous, ridiculous number of people. But the human population of these 30 universes will match the number of water molecules in a single drop of water. So a mole is exponentially large and an atom is exponentially small. Just saying the phrase "it's exponential" is not very descriptive. All right. So quantum eraser, remember that time, we were walking in the sauna and my towel fell off. Did you remember what you said?
Exponential.
So it's like, wow, I'm quite impressed by that. Oh, you know what? Exponential isn't very descriptive. Is it exponentially large or exponentially small? What did you mean?
You can't even put this in your mind how big this is.
Oh, okay. That's much better. Thank you. Let's move on to scientific notation. All right, so you guys all know what scientific notation is. You've got some number between 1 and 10. It has to be less than 10. So 9.999 is like the highest number you can use. And then you've got a 10 to the something. Now that has to be an integer. So either positive or negative counting numbers. All right, and there's some examples of positive integers of 10 or positive exponents of 10, negative exponents of 10. All right, you guys know this, but what we're going to focus in on are these negative powers of 10, which gives us really, really small numbers. So let's take the number line. This is actually a centimeter ruler, but let's take the number line from 1 to 10 centimeters, or 0 to 10 centimeters, and let's ask, where is 10 to the negative 1 on this number line? Well, that's 1/10. All right, so that would be right here. Now let's stretch the number line out so that the number line goes from 0 to 1. Okay, so we adjusted our red arrow a little bit. And let's ask another question. Where is 10 to the negative 2? Well, that's 1 over 100, or the arrow would be pointed here. Okay, and let's go even further. Where's 10 to the negative 3 on this number line? Well, that's 1 over 1,000. That's going to be really, really, really close to that 0. So as your negative exponents get larger in size, the actual values get closer and closer and closer to 0. Okay, let's talk about the notation of scientific notation. So this is Avogadro's number. So you got some number times 10 to some power. And if you write it using a typewriter, so if you're just like typing a text message to somebody or an email, you can use that caret. So Shift-6 gives you the little caret symbol. Or you can use a little bit of shorthand. You can use the letter E to represent times 10 to the. All right, and then the plus sign's kind of optional. I like to use a capital E so it doesn't look like Euler's number. Now there's a couple mistakes that you can make with this. So one is to kind of mix and match these two notations. So E and then the caret and then the 23. That looks like you're raising Euler's number to the 23rd power. Or what if you just forget the E? Instead of using an E, you use a caret. All right, so this means 6.02 raised to the 23rd power. That is not scientific notation. We are not multiplying that by 10 to the 23rd. Okay, and also positive and negative exponents are not interchangeable. Now, the reason why I'm covering these is because you will see them later in our presentation with Quantum Eraser. And now, next is decimal notation. If you have lengthy decimals, it's really hard to just read the decimals. So if it's more than 3 decimal places, you want to space them out in groups of 3. And you'll notice that Blue Marble Science did this correctly when he analyzed Quantum Eraser's subtraction error. All right, you space out your decimals in groups of 3. That makes it much easier to read. Okay, so on Quantum Eraser's toe tag of me, he had this presentation where he's talking about 10 to the negative 8, and then he's talking about 10 to the negative 17. And then just literally 2 seconds later, when he scrolled down, he's making fun of me for saying that the word exponential triggers people to think really big numbers. I mean, he's giving me a hard time. Okay, but then he writes 100 million, but the original number was 10 to the negative 8, and then he writes 100 quadrillion, but that was 10 to the negative 17. So it's like he himself is getting confused by these negative exponents and treating them as positive exponents. Now on this screen, he's diving in. He's doing this interesting math problem with a box, and then he's got a sea level box and an outer space box. But he's pointing to this one number, and it's got a pink 0, and he correctly identifies the pink 0 is in the 100 trillionths place. Notice the TH, 100 trillionths place. That's 10 to the negative 14. He did that correctly. But then he points to this 1, and he calls that the 100 quadrillions place, but that's 10 to the 17, not 10 to the negative 17. So again, it's like he's mixing and matching positive and negative exponents as if they were the same thing. So repeatedly, Quantum Eraser told me that numbers like 0.0000001 weren't close to 0.
This number right here isn't close to 0. This is one part in 100 million. And even smaller, this is one part in 100 quadrillion. How close to zero is that?
So let's actually analyze this from the standpoint of a teacher. So what exactly did quantum eraser mean when he said this? So he's pointing to this really tiny number, and he's like, this number isn't close to zero. So can you use the principles of diagnostic teaching rather than just casually dismissing his mistake? And I'll be honest, the first time I saw that,
You're an idiot!
that's what I thought, all right? I immediately thought of Judge Judy, okay? But let's not think like Judge Judy. Let's just not dismiss him as an idiot. Let's actually ask, what is his thinking? So let's think like a teacher. The student has made a mistake. What was the mistake the student made? So there's your challenge. And I will confess, it took me multiple times of watching that video. I was making this presentation, so I had to watch it over and over and over again. And it finally hit me what his mistake was. He wasn't just pointing to the number. He was pointing to the distance between the red 0, and that 1. So we have 10 to the negative 8, and that's far from 0 visually. Right? And then he goes even further. He's like 10 to the negative 17th. Well, how close to 0 is that? So here's 10 to the negative 8. Well, that's even further from 0. Okay, so you see how visually that this might be a misunderstanding, a point of misunderstanding. So let's go back to this scientific notation. As negative exponents get larger in size, the actual values become closer to 0 on the number line, which is how we compare numbers. Right? We compare them on the number line. Okay? And so really this is the key to diagnostic teaching, is taking the time to understand a student's mistake, especially if the student is trying, and doubly so if the student genuinely believes his answer is correct. And you could tell from Quantum Eraser's demeanor that he thought he had 100% of that done correctly. So I'm going to make an analogy here, and I don't know if you've seen the movie The Cannonball Run from 1981, but there's an actual race. It's sort of an undercover race. It's not an actual race with referees, because it's all done illegally because you are breaking the speed limit in every single state. But it is a race that goes from the Red Ball Garage in New York City to a very specific hotel in Los Angeles. And the reason why I'm raising this is because recently, because of the coronavirus and like the lockdowns, a lot of the highways have been open. And so the Cannonball Run has been broken. The record has been broken multiple times in the past 2 months. All right. So let's use this as an analogy for our number line. So we're going to start our number line at Red Ball Garage. That's the starting point of the Cannonball Run. We're going to end up at the Portofino Hotel, which I believe is Redondo Beach, California. And so as the crow flies, it's 3,960 kilometers. Obviously, the driving distance is much further. But so what we're going to do is we're going to take the entire United States, and we're going to put it between the numbers 0 and 1 on the number line. Okay? So here's the United States. We're going to plunk down the world's largest number line so that 0 is at the Red Ball Garage, 1 is at that hotel in Los Angeles. Okay, so here's the Red Ball Garage. There's the end of the number line. There's the number 0. And let's actually talk about the numbers that Quantum Eraser was talking about, the numbers he said weren't close to 0. So the number was 1 part in 100 million. How far is that? That's going to be 4 centimeters away from the Red Ball Garage. And 4 centimeters is about the distance, or if you put a penny and a nickel next to each other, that's about 4 centimeters. Now, what about that 10 to the negative 17? He's like, well, how close to 0 is that? Well, it's 40 picometers from 0. That's how close. And what's 40 picometers? It's smaller than a hydrogen atom. Okay, so these numbers are very, very close to 0. So let's do a bit of a review. We've covered a number of topics so far. And what I want you to do is find 7 problems in just this one screenshot. So let me zoom in a little bit so you can see the details a little better. Feel free to pause the video. See if you could find 7 things wrong, ignoring duplicates. If you do include the duplicates, it's even more. What are 7 errors? Well, first we have two different scientific notation fails. Here we have E, but then there's that caret, so that means E raised to the negative 19 power. And then here we have the missing E, so he's using shorthand, but, it's just very confusing. Decimal notation, so apparently he never learned that if you type out a long decimal, you have to space between groups of 3 decimal places, okay? And it's very, very hard to read any of his numbers in the entire presentation because he never does this. 2 more fails, significant figures. Now, these are 2 different fails. So the top one, he's converting from torr to PSI, but there's only one significant digit. 10 to the negative 17 torr has one significant digit. So his final answer should have had one significant digit. And then down below, subtraction, he should have had 4 significant digits with that, and he's just writing them all out. All right. And then number 6, he's using that exponential move phrase, which does not have a definition. All right. And then lastly, number 7, that subtraction fail that we went over at the beginning. All right. Now I added a bonus one.
Now what?
Misplaced arrogance.
Now what?
Oh, goodness. With a little face palming emoji, right? All right, let's move to our next section. So here's a challenge for you. If you had a mercury column, 1 inch square and 760 millimeters tall, what would that weigh in pounds? And, assume that everything's measured very precisely. So we got 3 significant digits, and I've got some data there to help you in case you wanted to use dimensional analysis. But I predict that there will be a whole lot of people in my audience who will know what this answer is off the top of their head without doing any math. Okay, that's my guess, is that there's going to be a bunch of people who are going to know the answer. And that may seem kind of cryptic. Like, how on earth would they know the answer? How would they be able to do this math in their head? Well, let's take a look at the math. So we got the height of the column, and then we've got the area of the base. Notice the different units. So let's get rid of square inches and convert that to square centimeters. So the square inches cancel. And let's convert centimeters to millimeters. So the millimeters cancel. And I hope you notice carefully, we now have cubic centimeters. All right, we now have cubic centimeters. So let's convert cubic centimeters to grams. So we now have grams. And let's get rid of grams and switch it over to pounds. If you multiply the whole thing out, you're going to get about 14.7 pounds to 3 significant figures. And like I said, I predict a bunch of people probably knew that off the top of their head. All right, so that is talking about air pressure at sea level. So we're going to talk about units of pressure and do a little bit more dimensional analysis. So what we're going to do is we're going to start with an excerpt from the start of my conversation with Quantum Eraser in 2016. Remember that green section. So do I explain where atmospheric pressure comes from? Do I explain the units of pressure? How many times do I say pounds per square inch?
The 15 pounds per square inch, or it's like 14.5 pounds per square inch, which is standard atmospheric pressure, which most people, who are listening to this are experiencing. That's a weight per unit of area. So 15 pounds per square inch. So literally, if you had something that was 15 pounds and then you had it, resting on a postage stamp on your hand, you're like, wow, that's pushing down really hard. 15 pounds per square inch. Well, what that is the weight of a column of air, literally 1 inch by 1 inch, that is 60 miles tall.
Okay.
And obviously, it gets thinner as you go higher and higher and higher and higher.
So there's your answer key. Now, a little bit later in our original conversation, he pulled up this document. It's a little blurry because I took a screenshot of a video. So the original was much clearer. But basically, he's got torr values at various altitudes. And I'll be very honest. To this day, I'm like 53 years old. I've got a math and science background. I have never heard anybody else in the world use torr besides Quantum Eraser. So,
are you looking at this, Charles?
Yes, flat Earth proofs, sea level, 760 torr. I guess a torr is a millimeter of mercury.
Look at these values here. We are talking about exponential values of pressure gradient.
Exponentially small.
Exponential. It doesn't matter how small. 10 to the negative 17?
Yes.
For interstellar deep space? Down to 10 to the negative 12? That's
But
exponential magnitudes of pressure gradient.
okay, well, no. It's
Yeah, it
no,
is.
because
It's looking at you right in the face.
So that was from our 2016 conversation. And notice that I was attempting to use precise language, exponentially small, and then when he used phrases like exponential magnitude, I said no, because exponential magnitude is not, well, what is exponential magnitude? So I did a Google search for it because I just wanted to cover all my bases. I wanted to see is there something that like I don't know that like is actually defined. And it turns out exponential magnitude isn't defined, but the closest I found was this video where they were doing some operations with Euler's formula, and they're trying to find the magnitude. And the way you find magnitude is you put absolute values around it, which is exactly what's happening at this screenshot. And Euler's formula is an exponential function because it has your variable. In this case, it's phi or phi in the exponent of e. So I don't think exponential magnitude is defined, certainly not the way Quantum Eraser is using it. So again, let's take a look at this timeline. This is our 12-minute chat. And again, those are the 4 clips that Quantum Eraser used in his toe tagging of me. And again, this diagram is to scale to the pixel. So there was that 1-minute presentation that I just showed you, the 1-minute presentation on atmospheric pressure, where I mentioned PSI 4 times. Now, we talked about a bunch of other things regarding atmospheric pressure, and especially like entropy and things like that. But here was my last mention of PSI. And then here's where he introduced torr. Okay. And then I introduced I mentioned 14.5 again, and I meant PSI. Okay. But he really had a hard time with me using PSI.
This doofus thinks he's clever and switches the units of measure from torr to PSI.
So did I switch the measurements from torr to PSI? Because I don't think so. So he kind of acted like PSI was very confusing. And the thing is PSI confusing and unusual? So here's your tire gauge, PSI. Here's a fire extinguisher gauge. It's in kilopascals and PSI. Hot water heater, PSI. Here's a HVAC kit, and the gauges that they use are really quite ingenious. Let's zoom into one of them. It has lots of readings that you can look at. The biggest and the boldest, yep, that's PSI. But then they also have things like kilograms per per square centimeter, which is very, very close to an atmosphere. And then you've got inches of mercury in a vacuum, and then centimeters of mercury in a vacuum. And then we've got one of his favorite insults. So, I'm not trying to make it seem like PSI is the only measure of pressure. There's tons of measure of pressure. We saw earlier, we saw pascals and we saw atmospheres and things like that. But my background is in engineering, so I'm a PSI guy. But when I was studying chemistry and biology, we used millimeters of mercury. But it's also called torr. In fact, they're not exactly the same. They're off by like a 1,000th of a percent because of the way they're defined. All right. And torr is named in honor of the guy who invented the barometer, Evangelista Torricelli. He died way too young. So, it's great that Quantum Eraser uses the word torr, but I just have never heard anybody else use it. But I was trying to find, are there any other mentions? Like let's look at medicine, right? And so I found this gauge. And what's a 16-letter word that starts with S and rhymes with thermometer? Can you get it? And can you spell it? It's a sphygmomanometer. Sphygmo refers to blood, and then manometer refers to pressure or measuring pressure. All right, so that's a blood pressure reading, and it's in millimeters of mercury. Here's a presentation from the American Heart Association. Again, they use millimeters of mercury. This is from the NHS in the UK. They use millimeters of mercury. And what about in medicine? What about the pressure of the air in your lungs? Well, they use millimeters of mercury as well. So even like medicine, chemistry, physics, it looks like a lot of people are using millimeters of mercury instead of torr. So, but nothing wrong with torr. Torricelli was a pioneer.
No. I think the PSI got everyone confused too, because I think that's what they try to do is confuse, right? They feebly try to do it, He tried to he didn't even interconvert the measurements. He's treating 14 point, whatever he said. What did he say? 14. He didn't even get that right. 14.5. He didn't even give us PSI here. Right? He's trying to get away from the exponents, but what he hadn't done was dimensional analysis, even within PSI. He didn't convert the 10 to the negative 17th to that equivalent in PSI. He didn't do that from torr to PSI. That's where he's all screwed up.
All right, so this, I can't let that go without comment. Let's take a look at this. So again, he's talking about how PSI is confusing everybody, and I really don't understand what a unit of measure that literally describes what it is, pounds per square inch, a 15-pound weight on a postage stamp. It's very, very descriptive. Now, nothing wrong with torr, but like torr is very hypothetical in comparison. So I'm trying to confuse. Well, listen again to our 12-minute conversation, and I copied it onto my channel, literally just the 12-minute conversation part. But the original is still on Robert Bassano's channel. Quantum Eraser has at least an hour and 45 minutes of our conversation. Try to find anywhere where I attempt to confuse anyone, and you'll be looking for a while. And then he's like, he didn't even give us PSI. Well, I didn't say PSI because literally 30 seconds earlier I did say PSI. I'd said it so many times in the minutes leading up to that statement. So I just said 14.5. Everyone should understand that I meant PSI. And then he says he's trying to get away from the exponents. No, I'm trying to explain the pressure differential is not exponential. It's 14.5 PSI. But he's got this thing with exponents. Dimensional analysis, it sounds kind of like a challenge, but I'll be happy to show you some dimensional analysis in the next couple slides. But he says, he didn't even convert. So I just want to remind you, we were having a live conversation. He gives me this document I'd never seen before. And so no, I was not going to convert from torr to PSI using mental math as we were speaking, which is kind of a silly, it's a silly expectation. As far as being all screwed up, it's a bit ironic. So he was challenging me to do 10 to the negative 17 torr, which is apparently the pressure in outer space, and he wants me to convert that to PSI. So I'll be happy to do so. So these are the numbers that he gave on a slide in his presentation, and he gave the value. So let's actually do the math. So we're going to convert between torr and PSI using his conversion value of 14.69, and we get 1.93289 times 10 to the negative 19 PSI. Now again, significant values, significant digits, we're not going to include all those digits. But what's interesting is that the value that he gives on his slide is slightly different. And I'm not saying that's a huge deal, because it's the thousandths place. That 3 is the thousandths place. So this difference is not a huge deal. But the question in my mind is, how did he get a different result? Because, we're all using calculators, right? So how did he get that different result? So what I did is I started with that, and I backtracked, sort of using detective work to reverse engineer what was his conversion factor. And I found his conversion factor was 14.695968 PSI, which is not a bad conversion factor. I'm not faulting him for that. That is a perfectly acceptable conversion factor. What I am faulting him for is that does not round to 14.69, which is what he presented in his original slide. Okay, so remember, Quantum Eraser, to round, if you see 5 or up, you have to round up. Okay, so your conversion factor, you should have given it, if you were rounding, you should have given it as 14.70. All right, but all that's irrelevant because the overall conversion to PSI should only have one significant figure, one significant digit. So it's 2 times 10 to the negative 19 PSI. Which means that we need to add one more thing, because that was from that slide. Remember that slide from earlier where we found all those fails? So fail number 9, rounding, facepalm. Okay, so I had talked about how sometimes people get triggered over, over big numbers. It was triggered over the word exponential. So he had this example of these two boxes. He had a sea level box and he had a vacuum of space box. Now, for some reason, he gave each box 100 quadrillion cubic centimeters, but he made this comparison and he said there would be 7.66 sextillion particles in the sea level box. So what's a sextillion? That's 10 to the 21st. Right, so we're gonna see that number in a couple slides here. Let's do a dimensional analysis with this 100 quadrillion cubic centimeter box. Now this is quite a large box. It's 10 kilometers by 10 kilometers by 1 kilometer. So that's 100 cubic kilometers. Okay, but anyway, I think I know why he picked this size box. But let's take a look at the size of this box. We'll start with the sea level box. And we first want to convert cubic centimeters to liters. So there's 1,000 cubic centimeters, or otherwise known as a milliliter. And that cancels out cubic centimeters. Let's go 22.4 liters per mole. And finally, we use Avogadro's number to come up with the total number of gas molecules. All right. And now let's do the deep space box. Now we're going to convert to cubic meters. And the reason why we're going to convert to cubic meters is because outer space, and I think it might just be a theoretical number, but they estimate that there's one gas molecule per cubic meter. So that's why I can convert it to cubic meters there. And that gives us 10 to the 11th. All right. Now these were his numbers for the sea level box and the outer space box. Now, how did he do compared to the real world? So we're going to have quantum erasers values, and then we're going to have the values that we got from basic chemistry. All right, and then we're going to see what his order of magnitude error is. So the sea level box, he said there'd be about 10 to the 21 particles, and we calculated it to be about 10 to the 36. So he's 15 orders of magnitude too small. The deep space box, he said it would have one particle. Now again, this box is supposed to be 100 cubic kilometers. And so that's 10 to the 11. So he's 11 orders of magnitude off. Now, what if he didn't really mean molecules? So notice on the red column, the quantum eraser, he talked about particles, and whereas, I was doing chemistry with molecules. So what if he didn't really mean molecules? What if he was just doing, trying to make a point about the ratio of what these values would be. So let's just do a ratio of the two boxes, just in case I got that misunderstood. So that's about 10 to the 21 to 1, and then this is a 10 to 25 to 1. So again, he's 4 orders of magnitude too small. So again, let's go back to diagnostic teaching. What was the error in his thinking? What was the error in his thinking? So that even the ratio of his boxes would be 1,000 or 10,000 times off from reality. So think about that for a moment. And it's because he assumed that pressure was proportional to gas particles. And anybody who's taken, chemistry or physics, especially if you had a good teacher who went deeper with it, you would have found out about this concept called a mean free path. So pressure is inversely proportional to the mean free path. Okay, so he had made a mistake there. Maybe he's never heard of mean free path, probably because he has not taken chemistry. But again, he didn't use dimensional analysis, so that definitely would have revealed his error very quickly.
This is as right as the rain.
And he calls this entire exercise right as rain. Well, I guess that depends on where you live. Anyway,
that's what's confusing here. It appears to be a lack of comprehension.
Yes, I agree, Adam. There appears to be a lack of comprehension. Now we're going to get into, this is really the thing that you guys have all been waiting for, is the topic of pressure differentials and pressure gradients.
How do we calculate pressure differentials?
Okay, so
that's
we're going
the question. Yeah. He's asked it for 4 years now.
Yep, I've asked it for 4 years, but let's actually explore. Let's actually derive pressure differentials. Won't that be fun? All right, so here's a quick challenge for you. Quick, what's 12 divided by 1/2? Go. Did you say 6? That's what most people say. The correct answer is 24, because 12 divided by 1/2 is the same as 12 times 2 over 1, which gives you 24. And the rule is when you divide by a fraction, you multiply by the reciprocal. So the ever larger denominator, if you're dividing by a fraction and the denominator gets really big, your actual final answer will get even bigger. All right. So let's keep that in mind when we think about, he kept going on about 10 to the negative 17 torr, right? So that really means 1 over 10 to the 17th, right? So he kept talking about 10 to the negative 17 torr, and he kept saying exponential. But why does it lead Quantum Eraser to think huge numbers? In other words, I want you guys to use diagnostic teaching to think about what his error in thinking could be, okay? And again, don't just say he's an idiot, right? Don't do the judge duty, right? I want you to think like a teacher. What is the actual mistake he's making? Now, this is one that I'm not 100% sure that I know. If I'm working with a student, I'd obviously, kind of tease this out a little bit more and try to probe a little bit and find the student's actual misconception. So I can only guess as to what Quantum Eraser's misconception is. And I came up with 2 guesses. One possibility is that when we do 1 over 10 to the 17th, that requires division. So without really being aware of it, it's possible that when he is thinking of 10 to the negative 17, he's actually thinking of divide by 10 to the negative 17. And when you divide by that very tiny number, you're going to get a big result. But there's another possible mistake in his thinking, and I think this is more likely, is that he's thinking about the strength of a vacuum, which there is no such thing as a strength of a vacuum. A vacuum is a lack of something. It's the strength of pressure, right? But he's thinking of the strength of the vacuum requiring the ratio of sea level pressure to outer space. So if you did a ratio of, in torr, 760 to 10 to the negative 17, that means you're actually going to be multiplying by 10 to the 17. Okay, so that might be his problem. He's thinking this ratio is it's exponential, right? But in reality, a vacuum is simply the lack of pressure. So you will subtract. Oops, I gave it away. So one analogy for pressure differentials is hydraulic equipment. All right, so I love hydraulic equipment, heavy equipment. This is a backhoe. Looks like it was freshly painted. I can't imagine that thing has seen a day of work out there with all that dirt. But how many hydraulic cylinders are visible in this image? So go ahead, click pause if you want to try this. There are 6. Okay, there are 6. And let's take one of these cylinders and let's actually analyze it. So there's fluid in front of the cylinder and there's fluid behind the cylinders. And both those fluids are under pressure. Obviously, you're going to have a lot more pressure on one side if you've got an outstroke or an instroke. Okay, so let's take a look at the outstroke where the red fluid is under more pressure. Okay, and the yellow fluid is actually just being expelled back into the reservoir. So the red side pushing on the cylinder, but then the yellow side, with a smaller pressure, is pushing on the rod side. So you got pressure on the piston side, pressure on the rod side. Now, here's where you think about the pressure. It's not just a pure pressure differential, right? Because the area is not the same. On the piston side, you have a full circle, but on the rod side, you have to subtract the area of the rod. It's a very clever little geometry problem, very simple geometry problem, but this little guide goes through the math. So you really are doing a subtraction of the forces. All right, so you subtract to find the force differential, and this is analogous to the pressure differential. All right. And again, he's talked about how every time I use PSI, I was trying to confuse people, but PSI is everywhere. At least a lot of the references that I saw. All right. Now let's change topics a little bit. What might be a pressure differential gauge? Like pressure differential is the topic of the hour, right? And what might a pressure differential gauge measure? Or how
would I subtract? And subtract from what, pray tell?
Well, I'm glad you asked because it says right here the differential pressure is the subtraction of F1 minus F2. All right, so the differential pressure is the subtraction, literally given on the instruction manual for this pressure differential gauge. All right. Now, under his toe tagging of me, there were some really funny comments, really interesting comments. And so one fellow made a comment, and Quantum Eraser gave this response, telling this guy he's the numpty of the millennium, telling him he'd be thrown out of a third grade math classroom. Not only that, but tackled by security. So I was curious, like, what on earth this commenter, what on earth he did that prompted this response. So I started thinking about what kids learn in third grade. So I just did a Google search, words for add, subtract, multiply, divide in third grade. And so the first 5 links had these 3 really nice posters, 2 of them handmade, right? And I kept seeing this word come up, this word difference. And it was always under the subtraction column. Difference, difference, difference. Here are more posters for classrooms. Difference, difference. Here are more posters. Difference, difference. And the poster on the left, it actually literally is from Adventures of a Third Grade Teacher. So every time they came up with the word difference, it meant subtraction. So what prompted this outburst by Quantum Eraser? So Matt Churchyard, in part of his comment, he said something like, there's a small difference between 10 to the negative 17 millimeters and 1 millimeter. The difference is less than 1 millimeter. All right, so Quantum Eraser's response is crying, laughing, WTF. It's 17 orders of magnitude difference. Now, we understand that doesn't make any sense. You can't have orders of magnitude difference. Difference means subtraction, period. Okay? So somebody would get thrown out of a third grade math classroom.
Why are we even subtracting?
Oh my goodness. Why are we subtracting? It's because to find a difference, it means to subtract. Okay? And here's a tip. Differential has the same root word as difference. Isn't that neat? Now let's talk about the Greek letter delta. All right. So the Greek letter delta, and believe it or not, I wasn't the first person to introduce this in this topic. It was, in fact, Quantum Eraser who introduced this. Let's take a look. This is an older video. I don't know exactly what the date is because he recently republished this as a premiere. So this was apparently Ballbusters episode 5. And he was talking about gas pressure versus gas pressure gradients. Now, what he means is pressure differentials. But people keep challenging him about how can you have a pressure differential? So he calls the gas pressure X and he calls the gas pressure gradients delta X. Now, really, he meant differentials. Okay, but he's using delta X, which is very interesting. What does delta mean? Delta means difference or change in. So delta Y is change in Y. All right. And here's an example of something with a heat exchanger. So you've got delta T, T2 minus T1. You've got a physics lesson, delta V, change in velocity, delta T, change in time. And they actually define them over to the right. It's final minus initial, delta. And this is a chemistry example, mass times specific heat times the delta T, or the change in temperature. And they even define it, final T minus initial T. So here's just yet another example, Quantum Eraser, why I think you should learn chemistry. Because I think you'd really
Why
get a lot
am
out
I
of it.
using subtraction for anything?
Oh my goodness. We just explained it to you. Why you're using subtraction is because it is the delta. It is the change in the pressure. So the delta pressure, change in pressure. Subtract final minus initial, or do it in whatever order you want. But please subtract.
How do we calculate pressure differentials, QE?
Okay, so we've gone over this like 12 times, but let's do another analogy. Let's specifically consider the question of division versus subtraction. So let's have some kids, and they're pushing on a rolling wall. So they've got some wall. The wall has got some rollers on it. And so what we have is we have a blonde-haired kid in the front, and then we have 2 sets of twins, kids with brown hair, kids with black hair. So they're pushing, and clearly, 3 versus 2. Clearly the blonde side team is pushing the wall. All right, but now let's take away one of the sets of twins. Right, they were canceling each other out, and still the wall moves to the right, obviously. And let's cancel out the other set of twins, and still the wall moves to the right, obviously. That's common sense. Okay, so let's take a look let's analyze this to see what we could do mathematically. So we have the 3 kids on the left and the 3 kids on the right. Now that weird symbol in the middle, I'm just meaning, greater than, less than, equal to, the question mark, right? So let's subtract the black-haired kid, all right? And now let's subtract the brown-haired kid. And what are we left with is the blonde-haired kid and then nobody on the other side. So what is the comparison? It's a greater than, okay? So let's take a look at these and let's use math. Let's use division, or I'm using a colon to kind of represent a ratio. So we have a 3-to-2 ratio, we have a 2-to-1 ratio, and then we have a 1-to-0 ratio. Now that hopefully is bothering a lot of people. You can't do a 1-to-0 ratio. That doesn't make any sense. How about subtraction? We have a 3 minus 2 situation, or a 2 minus 1 situation, or a 1 minus 0 situation. So which one of these things gives us consistent results? And specifically, since 1 divided by 0 is undefined, it is subtraction. So clearly, pressure differentials will be done with subtraction. Okay?
I'm not subtracting anything.
Oh my goodness.
You knuckleheaded bozo. I'm comparing values and identifying exponential moves.
All right, so I've already explained this like 7 times. You have to subtract because that's how you find pressure differentials. If you want to just compare values, normally people compare values with inequality operators, okay? And exponential moves, that simply is not defined. So please stop using that phrase. Now, here's a brief segue into the rules for men. Number 29, your arrogance to knowledge ratio should be much less than 1. Now, your ratio might be bigger than 1 if you have like a whole lot of arrogance, but your ratio will really go sky high if you're dividing by a fraction. All right, so let's do a practical application of pressure differential. And we're not actually going to talk about the de Havilland comet, but it's a tragic tale of history of technology and their wings, or I'm sorry, their square windows. But we are going to talk about modern commercial windows. So let's ask the question: what is the pressure differential on a commercial plane's windows? All right. So I first asked, what do they fly at? What altitude do they fly at? And I'm going to round this up to 40,000 feet. Private jets, corporate jets fly higher, 43,000 feet. So I grabbed this chart off the internet. So sea level, and then we've got some high altitudes. And what we're going to focus in on is PSI, because this kind of makes sense, pounds per square inch. 14.7 versus 2.7. All right, so what's the differential? 12 PSI, right? That's how you find the differential. So you subtract. So let's take a look at a couple aircraft windows. We're going to go to the one on the left, the Airbus 330, because it has a nice 100 square inch surface area. So we have 12 PSI, we have 100 square inches of area. That gives us 1,200 pounds of force. People probably didn't realize that when you're at cruising altitude, there's 1,200 pounds of force pushing on that window, trying to push that window out of the frame. Okay? But the thing is, this concept is what causes a lot of people to think that manned spaceflight can't be possible. Like there's no way that Apollo could have flown because of the exponential, vacuum of space.
Exponentially stronger vacuum and exponentially weaker gravity.
Okay, so people think, that space travel is not possible, specifically manned space travel. So let's actually do the math with Apollo. And let's do a very specific commander's side window on the Apollo command module, and which flew with about 5 psi of atmosphere. So first thing we want to do is find the pressure differential. All right, so if you use mental math, 5 minus a ridiculously small number, all right, rounded to the nearest psi, the answer is 5. All right, 5 psi. All right, that's the pressure differential on the window. And let's take a look at this window. If you look very carefully, it actually has a gauge on it. I think that was used in navigation. But this is actually from an auction where some old Grumman employee had a spare, window from the Apollo module. I don't know what it sold for, but it did sell. And so using a triangle calculator, it's 210 square inches. So we have 5 psi, 210 square inches. I like to make tens. Like I'd like to do mental math, when I can. So it's like I divided the right by 2 and I multiplied the left by 2 to kind of make the math easier. So we have 1,052 pounds of force. So it's amazing to me that the windows in the Apollo command module in outer space would have less pounds than the windows on an Airbus 330. And in my research, I came across this document, which is really fascinating because it really breaks down all the different windows and the layers. And specifically, they cover, which layers are under vacuum and which are pressurized. Fascinating stuff. So let's do a kind of a thought experiment, all right? And stainless steel straws have been all the rage because, plastic straws are apparently the worst thing ever. So let's take a stainless steel straw and let's have it be a standard drinking size straw, not a big thick milkshake straw, but a standard drinking straw. And let's punch it through the bulkhead of the ISS. All right. So it is starting to quote unquote suck the atmosphere into outer space. Okay. They're in orbit. All right. So what do? If you were an astronaut, you would stick your finger over the end of the hole. Okay? So the question is, what would be the result if an astronaut actually did this? So A, the astronaut would be liquefied, finger in hand first, and sucked out to space with the exponential vacuum. B, the astronaut's finger would be stuck to the straw with a great deal of force. C, the astronaut would be able to remove his finger easily, and it probably wouldn't even leave a mark. Well, let's do the actual math. So a standard straw, I actually measured a straw from Wendy's. So I didn't measure a stainless steel straw, but I did measure a standard drinking straw. So 2 millimeter radius, we've got the area, pi r squared, and convert to inches, that's 2/100ths of an inch. 2/100ths of a square inch is the opening. Now, cabin pressure, apparently the ISS, they operate at sea level air pressure. So 14.7 psi. The pressure of space is approximately 0 psi. What's the pressure differential? 14.7 psi. And we're going to multiply that by the area of the opening. And what do we get? About 4.6 ounces. That's about the weight of a small ring of keys. Okay? That's how much force would be on the astronaut's finger. So the correct choice was choice C. The astronaut would be able to remove his finger easily, and it probably wouldn't even leave a mark. Okay? And this reminded me of a story, a little inside movie story. If you ever saw the movie A Christmas Story, there's Ralphie there on the right. Somebody dares the character on the left to lick the flagpole in the dead of winter. Okay, and then so he licks the flagpole, and obviously he gets his tongue stuck. And so I'm interested in movies and I'm interested in how they're made. And I've always been wondering about like how they filmed this scene, because you're not going to get a child actor and have him lick a frozen flagpole. Okay, so what they actually did is they had a vacuum pump. They drilled a hole in the pipe. They ran the vacuum pump, and they had the actor. He sticks his tongue out, and it instantly sticks. And probably didn't leave a mark either. All right. So Quantum Eraser keeps talking about pressure gradient. So he uses the word pressure gradient when he really means pressure differential. But I was curious as to like what exactly is a gradient. What are gradients anyway? And the definition of a gradient is the change in one value over distance. So slope. There's a diagram for slope. But so slope could be rise over run, or change in one value over change in the other value. But a gradient is specifically over distance. Change in one value over distance. So in roadways, well, the change in elevation is measured over the change in horizontal distance. But you can measure them both in feet. You can measure them both in yards and in meters. So the units actually cancel out, which leaves you with what they usually use, percent grade. So whenever you see a percent grade, so 100% grade would be a 45-degree angle, right? Because you'd be rising, rise 1, run 1, right? So there's percent grade for roadway. There's a concentration gradient, and there's also pressure gradients. So let's take a look at concentration gradients. And these are used in chemistry and biology to describe why particles, like solutes, tend to move from high concentration to low. Now, when I was doing the research for this, I found that they would use the phrase concentration gradient, but they never have people calculate it. So it's very rare to have people calculate. So oftentimes people say there's a concentration gradient, and all they mean is, the concentration is higher over here and lower over there. They're not actually talking about the distance. But the definition of concentration gradient is the change in concentration divided by distance. So you're always dividing by distance. So there you go in chemistry, like if you sprayed, the analogy is if you spray perfume in one corner of the room, eventually you'll smell the perfume all over the room. And then in biology, you've got, these little molecules, and they're crossing the phospholipid bilayer. So what is a pressure gradient? So I know what a pressure differential is, and we've derived it, but I got curious because Quantum Eraser kept mentioning it. So I actually typed this into to Google. So I typed, how do you calculate air pressure gradient? And I hit return. And this is what it came up with. And I'm going to zoom into this on the next slide. The pressure gradient can be determined mathematically by taking the difference in pressure between two locations in pascals and dividing it by the distance between the two locations in meters. It's the difference in pressure over distance. Okay, very interesting. So let's do, and it's pascals. It's pascals per meter is the units, the SI units. So let's go from sea level to the edge of space, the Kármán line. Okay, so those are the distances, and I'm not rounding anything. It's a very good, when you're doing a multi-step problem, don't round your numbers in the middle of the problem. That's actually a very common error. Leave a bunch of decimals on there, and then you could always round at the very end with your significant digits. Okay, so the Kármán line is at 100 kilometers, so that's a distance of 100,000 meters, and we're going to divide these. And that's a mental math division, right? And we get 1.01 pascals per meter. So compare this to what Quantum Eraser says pressure gradients are.
The pressure differential.
Exponential magnitudes of pressure gradient.
No, that is absolutely false.
It's absolutely true. I just showed them to you.
All right, the pressure gradient, sorry, Quantum Eraser, but the pressure gradient is not exponential. Okay. But in actuality, I mean, I'm all kidding aside, air pressure gradients are not used vertically. They're not measured using vertically. They're used in meteorology when studying high and low air pressure systems. Okay, but again, the pressure gradient would be horizontal, and they're shown by those lines on the map. But the point I'm making is that Quantum Eraser has used this term, pressure gradient, for years, and he's never looked it up. He just uses it, and he just it's like he guesses that he knows what it means, but like he's never taken the trouble to look it up. That's where I come in. But so my one mistake, so you can take a look at that entire conversation I had, the 12 minutes on pressure or the whole 4-hour conversation. And so I will say that, my one mistake during the conversation on pressure was the one time I mentioned pressure gradient, and I really meant to say pressure differential, but it was impromptu. I said it once. So this is from our 2016 conversation, but this is a clip that is excerpted from his toe tagging video of 2020.
John, the pressure gradient between the Earth's surface and outer space is 14.5. It's not exponential. It's simply 14.5.
Can you believe that? Bearded numpty dipshit. John, the pressure gradient between the Earth's surface and outer space is 14.5. What does that even mean?
So I was thinking, I felt a little bad that I'd missed an opportunity to explain to him, in 2016, I missed the opportunity to explain to him what a pressure gradient or a pressure differential was, where the 14.5 may have come from and how we're subtracting and why we're subtracting and what are the two numbers. So I felt bad that, that was a teachable moment, and I let the moment pass. So what I did is I went back to the original Robert Bassano recording, and this is what I found.
John, the pressure gradient between the Earth's surface and outer space is 14.5. That is not
the pressure gradient between the Earth's surface
and say deep space.
8 torr to 10 to the negative 17th torr.
Yes, now subtract those. And what do you get?
You subtract them.
Yes. That's a differential, right? How do you find a differential? You take it, initial minus, minus final, or you could take final minus initial. The way you find a differential is you take two values and you subtract them. That's the differential. And what is the pressure differential between Earth's surface and outer space? It's 14.5. It's not exponential. It's simply 14.5.
So are you telling me that I had defined carefully pressure differential as a subtraction way back in 2016? I've been spending 4 years teasing this guy. How do you compute pressure differentials? And it was in the original conversation, but get this. And he edited it out. He literally just took the first few words and the last few words and he edited out the part where I defined pressure differential. That is what I call ironic.
So no, Charlene, it's not 14.5.
Well, I will say this, Quantum Eraser, that you are correct. It is not 14.5. It is actually 14.7 psi, the pressure differential between sea level and outer space. So thank you for correcting me on that. So Quantum Eraser, how do we calculate pressure differential?
Ask me that question again.
That was in his toe tag video. And what was really funny is in the live chat, when he said that, he got a nice response. I love the reference to Magic Eraser. Oh my goodness. All right, let's do a quick math overview.
This is such a train wreck of epic proportions. It's difficult to encapsulate in language.
Yeah, but I'm gonna try. I'm gonna try. So when doing multi-digit subtraction, you can't borrow from zero. If you subtract two positive numbers, you should not get a larger number. Significant figures are important when dealing with large and small numbers. Your answer will only be as precise as your least precise input. Scientific notation is used to express very large numbers or very small numbers. Very small numbers are, in fact, close to zero. And using precise language and terms can be very helpful in communicating. There are at least 7 well-defined terms using the word exponent or the word exponential. So please don't use exponential as a generic adjective to describe numbers, operations, or worse yet, moves. Pressure is a force or a weight per unit area, such as pounds per square inch. Pressure differentials are found using subtraction. The pressure differential between sea level and outer space is about 14.7 psi or 760 torr. And lastly, pressure gradients, in contrast, are found by dividing the pressure differential by distance. All right, so that's a pretty good summary.
I think this is a slam dunk, though, because you can't be this stupid.
So, John, I don't know if you went to college. I don't know if you did go to college, maybe you majored in music. Now, I'm not ripping on music majors. My mother was a music major. She then had a wonderful career as a piano teacher and choir director. For all I know, John, maybe you are a piano teacher. But please take a course in chemistry. Oh my goodness, please take a course in chemistry. This is a table of contents from I think a kind of a lower level high school textbook. But it'll cover the basics for you. For example, thinking like a scientist, and then specifically scientific measurement, where you just had so many issues with measurement, units of measurement, solving conversion problems, etc. A little bit of math in there, but please learn some chemistry. That's my advice to you. So let's take a look at the first law of rebuttal videos. And it goes like this. Be extremely well versed in the topic, the source, the video, or the person you're rebutting. And Quantum Eraser was 0 for 4 on this. Okay, be extremely well versed. So I'm going to give you a comparison to back 2 years ago, March 2018. Red's Rhetoric and Astronomy Live triangulated the distance to the ISS, and they recorded a video. Actually, each of them recorded a different video on it. But Dr. Zach debunked it right? Without apparently having the first clue what was going on. It didn't even appear as though he watched the full 14-minute Red's Rhetoric video. So I recorded a breakdown of where Dr. Zach went wrong, which was pretty much everywhere. It took 37 minutes to go through. So that video ended with this sequence featuring Joe and Reggie. So here's Joe. Joe has a YouTube channel, and Joe's interested in spelunking. So he records a video called Spelunking 101. Okay, it's just a hobby. And maybe he made some mistakes, maybe not. You know, it's nothing casual. So here's Reggie. Reggie also has a YouTube channel, but he records a video called Spelunking 101 Debunked. Now, this is not just a case of two guys with two YouTube videos at all, because Reggie is debunking Joe's video specifically. So is he questioning Joe's integrity? The bar is set much higher for Reggie than for Joe. Again, Joe is just doing something, hey, here's my hobby, you know, but Reggie is specifically going after Joe. So Reggie must watch Joe's video carefully, understand it completely, and be 100% sure that Joe is wrong. Okay? Now, let's take a look at our situation. We got Flat Earth Math, we've got Quantum Eraser, and Flat Earth Math was in a live impromptu conversation. I did not know the topics that would be covered, by the way. And Quantum Eraser, he had a prepared list of, you know, his multicolored documents. He had one of those prepared. So, you know, he was prepared. I was speaking impromptu. But not only that, in his sort of his toe tag of me, he had a prepared and organizing debunking document, and he had a 90-minute show. So for him to debunk me specifically, the bar is set much higher for Quantum Eraser than for Flat Earth Math, right? Quantum Eraser must listen to Flat Earth Math's points carefully, understand them completely, and be 100% sure that he's wrong. All right, so here's the thing, John. You had 4 years to prepare. It was a 12-minute conversation on atmospheric pressure. You could have re-listened to my description on how to compute pressure differentials like I've been teasing you for years now. And mathematically, you didn't appear to get a single thing correct in your 90-minute presentation. But throughout the whole presentation, you kept asking, and you're a math teacher? So somehow that makes me the numpty the dipstick. So that's a bit ironic. I love this comment underneath Quantum Eraser's toe tagging video. The first rule of Dunning-Kruger Club is that you don't know you're in Dunning-Kruger Club. All right, lessons learned. So Quantum Eraser and his panel, they mentioned my career more often than my LinkedIn profile. So what I did is I compiled a bunch of photos of students and schools where I've taught, and I'm listing the courses that I've taught.
The high school math teacher? And you're a math teacher? Would a math teacher know this?
Does this math teacher?
That he's a math teacher and doesn't know exponents. Mr. Math Teacher, and you're a math teacher. You teach our kids. This is a high school math teacher.
A math teacher.
Math teacher.
Charles, is a high school math teacher. A high school math teacher.
Yes, I am a high school math teacher, but I've also taught middle school computer science. And I've taught a few science. I'm dual certified math and science. So sometimes a school will tap me to teach biology, chemistry, or physical science. But this doesn't make me an expert. You know, I never claim to be an expert. If you watch any of my videos, watch any of my hangouts with people, I never, ever claim to be an expert. Doesn't even mean you should trust me. Okay. In fact, I ask people, don't take my word for it, you know. But it does mean that it is folly to assume that I do not know what exponents are. Okay? So if you feel that I'm saying something ridiculous, but you don't believe I'm an idiot, consider the possibility that you misunderstood, right? That happens. All right? So I'm not an expert at car engines or transmissions. Like, I'm a math teacher. I'm not a mechanic. So let me give you a quick example. So way back when all cars were stick shift, back when I learned to drive, If you pushed on the gas, that had a linear relationship with engine RPM. You push the gas down, the engine revs up RPM. And it was, in the older vehicles, there was a direct mechanical linkage between that pedal and your carburetor. All right, so a car's engine, an internal combustion engine, has a limited range of RPMs where it's efficient. It's not efficient at low RPMs. It's not efficient at super high RPMs. Actually, that's bad for the engine. So you've got this sweet spot of where the engine has the most efficiency. So you have, first gear, and then you rev up the RPMs, but then you hit the clutch, drop down, you drop your RPMs down by releasing your pedal, put it in second, but then your car speed is increasing the whole time, even though you're dropping into, you're dropping your RPMs each time, okay, because of that gas pedal. Well, now this means that automatic transmissions are not possible, because when you're driving an automatic transmission, your foot is on the gas and your foot does not move, and the car is shifting into other gears. Okay, so I'm going to just declare that automatic transmissions I just don't think they're possible. So I have two options. One of them is as a novice, I could argue against an expert, a mechanic. I don't think you understand how cars work, says me with the bow tie, right? Or option number two, I could learn, I could study, I could ask questions from experts. Okay, so Quantum Eraser, which of these options do you think you should take?
I also want to thank Flat Earth Math. What's your name?
Charles.
Is it okay if I call you Charles?
Please.
Yeah, I want to thank Charles for
John?
coming in, because it shows some intestinal fortitude to come in here. There's a lot of people that wouldn't have done that. I just want to recognize that.
So that was the first few moments of me meeting Quantum Eraser. And I just want you to pay attention to his tone, pay attention to how he speaks to me. So this is a little excerpt from a little bit later on.
He did say that you had some questions, and I'd be really happy to answer any questions, or just have a discussion.
Yeah, I just want to have a discussion. Like I said, I'm pretty impressed with you so far, even without listening to anything that you had to say. Just coming in here is impressive enough for me.
Thank you, I appreciate that.
Yeah, and just a discussion, because what we're after here is the truth. I'm sure we're all after that. I know a lot of people, it seems, and on both sides, not only Flat Earth or the Globe Earth, get bogged down in these petty, childish arguments, and it's real easy to tell that they're not after the truth. It's like an agenda or something, right?
Yes.
Do you agree with that?
Yes. And
I think it's equal on both sides, and we're adults here. I mean, you're a math teacher, right, for a high school?
Yes.
Now that's a respectable profession. I mean, and obviously you're an adult. We should treat each other with respect, common courtesy, which I see being lost a lot of times, and I think that would go a long way.
I agree. That will go a long way. Now, I want you to contrast that with this clip from his toe tagging video in May 2020. So it's 4 years later. And specifically, he really embodies the concept of projection. So projection was coined by Sigmund Freud, but the concept is actually, you could find examples in the Bible. So projection is a defense mechanism, attributing one's own thoughts, feelings, or motives to another. For example, an angry man might accuse another of being hostile. A con artist might be under the impression that everyone is trying to con him or her. So take a look at the examples of projection and just take a look at the difference in tone.
He should know this stuff, and he is purposely, with intent, attempting to deceive. I challenge anyone to challenge me on that conclusion. Here's my conclusion. You should be flogged. Yeah? Then friggin' hung from a yardarm for crimes against humanity. I'm serious as a heart attack. I'm tired of your shit. I'm tired of you numpty dipshits coming into this arena and crossing lines. Right? I'm sick of it.
No need to be sick of it, but know that I will never use profanity towards you. I will never use violent language or threats against you. And just remember, your lack of understanding doesn't make me a liar. That's why I encourage civil discourse. No yelling, no profanity, no insults, no muting, and no interrupting. And John, you are welcome to come on my civil discourse anytime. You can actually look at the previous, I think it's 15 episodes of Civil Discourse, and you will note that I never have used profanity. I've never muted anyone. So it is a very calm, reasonable medium to have a conversation. So you're welcome. You're welcome to come in. But here's a question for you, John. Why all the middle school insults? Like, when adults insult each other, I mean, they usually come up with like adult, like salty language, whatever. But a lot of your insults they're straight out of middle school. Numpty dipstick, bearded Charlene. Like, my name is Charles, and it's like you're calling me by a girl's name. Like that is literally straight out of middle school. Abject moron, crayon muncher. All right. Don't you forget that I've taught in inner city public schools for almost 25 years. And so there's two things that I want to say about that. One is I have very thick skin. I mean, the population that I teach, these are underserved kids, high poverty kids, and they've thrown everything at me, like literally and figuratively. So I've got very, very thick skin. But the second thing, and I think I need you to pay attention to this, I see who's making these insults. Who uses the insulting language when they're speaking to either me or their peers? And it's the most insecure of all the students. The kids who have the most insecurity, the least self-confidence, they're the ones that feel the need to insult so much. So I've come up with the golden rule of insulting people. And I think this applies, it may apply to your situation. Truly happy people don't treat each other like garbage, okay? I don't know of any violations of this rule, and it is written in gold. So, John, you're welcome to have a conversation with me if you want to talk flat Earth. I mean, that's great. We can have a good time. But, do you think maybe you should take a vacation from all this childish insults? Because, whenever you're insulting like that, I mean, you really look small.
I'm taking a vacation.
That's a good choice. Okay. So seek first to understand, then to be understood. That is in Stephen Covey's 7 Habits of Highly Effective People. And I think a lot of people, when they're arguing in the flat earth arena, is they're trying to jam their point down the other person's throat, and they don't try to actually understand what the other person's saying. So as always, your comments are welcome. Sometimes people, get kind of salty in my comment section, and just keep it civil. Don't insult people. Don't belittle them or, yell at them. Just try to seek for understanding. Please, above all, be kind to each other. Thank you.